The heading indicator is fundamentally a mechanical instrument designed to facilitate the use of the magnetic compass. Errors in the magnetic compass are numerous, making straight flight and precision turns to headings difficult to accomplish, particularly in turbulent air. A heading indicator, however, is not affected by the forces that make the magnetic compass difficult to interpret. The rotor turns in a vertical plane, and fixed to the rotor is a compass card. Since the rotor remains rigid in space, the points on the card hold the same position in space relative to the vertical plane of the gyro. As the instrument case and the aircraft revolve around the vertical axis of the gyro, the card provides clear and accurate heading information. Because of the precession caused by friction, the heading indicator creeps or drifts from a heading to which it is set. Another error in the heading indicator is caused by the fact that the gyro is oriented in space, and the Earth rotates in space at a rate of 15 degrees in 1 hour. Thus, discounting precession caused by friction, the heading indicator may indicate as much as a 15-degree error per every hour of operation. Some heading indicators, referred to as horizontal situation indicators, HSI, receive a magnetic north reference from a magnetic slaving transmitter and generally need no adjustment. The magnetic slaving transmitter is called a magnetometer. Electronic flight displays have replaced free-spinning gyros with solid-state laser systems that are capable of flight at any attitude without tumbling. This capability is the result of development of the attitude and heading reference system, shown above. The AHRS sends attitude information to the PFD in order to generate the pitch and bank information of the attitude indicator. The heading information is derived from a magnetometer, which senses the Earth's lines of magnetic flux. This information is then processed and sent out to the PFD to generate the heading display. The lines of flux in the Earth's magnetic field have two basic characteristics. A magnet aligns with them, and an electrical current is induced or generated in any wire crossed by them. The fluxgate compass that drives slave gyros uses the characteristic of current induction. The flux valve is a small, segmented ring, like the one above, made of soft iron that readily accepts lines of magnetic flux. An electrical coil is wound around each of the 3 legs to accept the current induced in this ring by the Earth's magnetic field. A coil wound around the iron spacer in the center of the frame has 400 Hz alternating current, AC, flowing through it. During the times when this current reaches its peak, twice during each cycle, there is so much magnetism produced by this coil that the frame cannot accept the lines of flux from the Earth's field. As the current reverses between the peaks, it demagnetizes the frame so it can accept the flux from the Earth's field. As this flux cuts across the windings in the 3 coils, it causes current to flow in them. These 3 coils are connected in such a way that the current flowing in them changes as the heading of the aircraft changes, shown above. The 3 coils are connected to 3 similar but smaller coils in a synchro inside the instrument case. The synchro rotates the dial of a radiomagnetic indicator, RMI, or an HSI. Remote indicating compasses were developed to compensate for the errors and limitations of the older type of heading indicators. The 2 panel-mounted components of a typical system are the pictorial navigation indicator, shown on top, and the slaving control and compensator unit, shown on the bottom left. The pictorial navigation indicator is commonly referred to as an HSI. The slaving control and compensator unit has a push button that provides a means of selecting either the slave gyro or the free gyro mode. This unit also has a slaving meter and 2 manual heading drive buttons. The slaving meter indicates the difference between the displayed heading and the magnetic heading. A right deflection indicates a clockwise error of the compass card. A left deflection indicates a counterclockwise error. Whenever the aircraft is in a turn and the card rotates, the slaving meter shows a full deflection to one side or the other. When the system is in free gyro mode, the compass card may be adjusted by depressing the appropriate heading drive button. A separate unit, the magnetic slaving transmitter, is mounted remotely, usually in a wingtip, to eliminate the possibility of magnetic interference. It contains the flux valve, which is the direction sensing device of the system. A concentration of lines of magnetic force, after being amplified, becomes a signal relayed to the heading indicator unit, which is also remotely mounted. This signal operates a torque motor in the heading indicator unit that processes the gyro unit until it is aligned with the transmitter signal. The magnetic slaving transmitter is connected electrically to the HSI. As instrument panels become more crowded and the pilot's available scan time is reduced by a heavier flight deck workload, instrument manufacturers have worked toward combining instruments. One good example of this is the RMI shown above. The compass card is driven by signals from the flux valve, and the two pointers are driven by an automatic direction finder, ADF, and a very high frequency, VHF, omnidirectional radio range, VOR. During pre-flight, check the heading indicator as the gyro spools up. Make sure there are no abnormal sounds. While taxiing, the instrument should indicate turns in the correct direction, and precession should not be abnormal. At idle power settings, the gyroscopic instruments using the vacuum system might not be up to operating speeds, and precession might occur more rapidly than during flight. One of the oldest and simplest instruments for indicating direction is the magnetic compass. It is also one of the basic instruments required for VFR and IFR flight. An aircraft magnetic compass, such as the one in Figure 7-30, has two small magnets attached to a metal float sealed inside a bowl of clear compass fluid similar to kerosene. A graduated scale, called a card, is wrapped around the float and viewed through a glass window with a lubber line across it. The card is marked with letters representing the cardinal directions north, east, south, and west, and a number for each 30 degrees between these letters. The final 0 is omitted from these directions. For example, 3 equals 30 degrees, 6 equals 60 degrees, and 33 equals 330 degrees. There are long and short graduation marks between the letters and numbers, each long mark representing 10 degrees, and each short mark representing 5 degrees. The magnets align with the Earth's magnetic field, and the pilot reads the direction on the scale opposite the lubber line. Note that the pilot sees the compass card from its back side. When the pilot is flying north, as the compass shows, east is to the pilot's right. On the card, 33, which represents 330 degrees west of north, is to the right of north. The reason for this apparent backward graduation is that the card remains stationary, and the compass housing and the pilot turn around it, always viewing the card from its back side. The magnetic compass is the simplest instrument in the panel, but it is subject to a number of errors that must be considered. The Earth rotates about its geographic axis. Maps and charts are drawn using meridians of longitude that pass through the geographic poles. Directions measured from the geographic poles are called true directions. The magnetic North Pole, to which the magnetic compass points, is not co-located with the geographic North Pole, but is some 1,300 miles away. Directions measured from the magnetic poles are called magnetic directions. In aerial navigation, the difference between true and magnetic directions is called variation. This same angular difference in surveying and land navigation is called declination. Above shows the isogonic lines that identify the number of degrees of variation in their area. The line that passes near Chicago is called the agonic line. Anywhere along this line, the two poles are aligned, and there is no variation. East of this line, the magnetic North Pole is to the west of the geographic North Pole, and a correction must be applied to a compass indication to get a true direction. The magnets in a compass align with any magnetic field. Local magnetic fields in an aircraft caused by electrical current flowing in the structure, in nearby wiring, or any magnetized part of the structure conflict with the Earth's magnetic field and cause a compass error called deviation. Deviation, unlike variation, is different on each heading, but it is not affected by the geographic location. Variation error cannot be reduced or changed, but deviation error can be minimized when an AMT performs the maintenance task known as swinging the compass. Most airports have a compass rose, which is a series of lines marked out on a ramp or maintenance run-up area where there is no magnetic interference. Lines oriented to magnetic north are painted every 30 degrees as shown above. The AMT aligns the aircraft on each magnetic heading and adjusts the compensating magnets to minimize the difference between the compass indication and the actual magnetic heading of the aircraft. Any error that cannot be removed is recorded on a compass correction card, like the one above, and placed in a card holder near the compass. The lines of magnetic flux are considered to leave the Earth at the magnetic North Pole and enter at the magnetic South Pole. At both locations, the lines are perpendicular to the Earth's surface. At the magnetic equator, which is halfway between the poles, the lines are parallel with the surface. The magnets in a compass align with this field, and near the poles, they dip or tilt the float and card. The float is balanced with a small dip compensating weight to dampen the effects of dip when operating in the middle latitudes of the Northern Hemisphere. This dip and weight causes two very noticeable errors: northerly turning error and acceleration error. The pull of the vertical component of the Earth's magnetic field causes northerly turning error, which is apparent on a heading of north or south. When an aircraft flying on a heading of north makes a turn toward the east, the aircraft banks to the right and the compass card tilts to the right. The vertical component of the Earth's magnetic field pulls the north-seeking end of the magnet to the right, and the float rotates, causing the card to rotate toward west, the direction opposite the direction the turn is being made. If the turn is made from north to west, the aircraft banks to the left, and the compass card tilts down on the left side. The magnetic field pulls on the end of the magnet that causes the card to rotate toward east. This indication is again opposite to the direction the turn is being made. The rule for this error is, when starting a turn from a northerly heading, the compass indication lags behind the turn. When an aircraft is flying on a heading of south and begins a turn toward east, the Earth's magnetic field pulls on the end of the magnet that rotates the card towards east, the same direction the turn is being made. If the turn is being made from south toward west, the magnetic pull starts the card rotating toward west, again in the same direction the turn is being made. The rule for this error is, when starting a turn from a southerly heading, the compass indication leads the turn. In acceleration error, the dip correction weight causes the end of the float and card marked N, the south-seeking end, to be heavier than the opposite end. When the aircraft is flying at a constant speed on a heading of east or west, the float and card are level. The effects of magnetic dip and the weight are approximately equal. If the aircraft accelerates on a heading of east, the inertia of the weight holds its end of the float back and the card rotates toward north. As soon as the speed of the aircraft stabilizes, the card swings back to its east indication. If, while flying on this easterly heading, the aircraft decelerates, the inertia causes the weight to move ahead and the card rotates towards south until the speed again stabilizes. When flying on a heading of west, the same things happen. Inertia from acceleration causes the weight to lag and the card rotates toward north. When the aircraft decelerates on a heading of west, inertia causes the weight to move ahead and the card rotates towards south. A mnemonic or memory jogger for the effective acceleration error is the word ANDS, acceleration north, deceleration south. Acceleration causes an indication toward north. Deceleration causes an indication toward south. Oscillation is a combination of all of the other errors, and it results in the compass card swinging back and forth around the heading being flown. When setting the gyroscopic heading indicator to agree with the magnetic compass, use the average indication between the swings. The floating magnet type of compass not only has all the errors just described, but also lends itself to confused reading. It is easy to begin a turn in the wrong direction because its card appears backward. East is on what the pilot would expect to be the west side. The vertical card magnetic compass eliminates some of the errors and confusion. The dial of this compass is graduated with letters representing the cardinal directions, numbers every 30 degrees, and tick marks every 5 degrees. The dial is rotated by a set of gears from the shaft-mounted magnet, and the nose of the symbolic aircraft on the instrument glass represents the lubber line for reading the heading of the aircraft from the dial. The outside air temperature, OAT gauge, is a simple and effective device mounted so that the sensing element is exposed to the outside air. OAT gauges are calibrated in degrees Celsius, Fahrenheit, or both. An accurate air temperature provides the pilot with useful information about temperature lapse rate with altitude change. Flight instruments enable an aircraft to be operated with maximum performance and enhanced safety, especially when flying long distances. Manufacturers provide the necessary flight instruments, but to use them effectively, pilots need to understand how they operate. As a pilot, it is important to become very familiar with the operational aspects of the pitot-static system and associated instruments, the vacuum system and associated instruments, the gyroscopic instruments, and the magnetic compass. This concludes your introduction to flight instruments. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.